Okay. So if you took notes on this last time, don't look at your notes. We'll just start over. Start over here, looking at this function related to this Ferris wheel. Okay, the associated units are meters, radians, and minutes. Okay, so this function f is given by f of t equals 28 cosine 3t. So each of these expressions, okay, ready to start? Ready to start? Okay, so each of these expressions, which are all part of this, the function rule, all have meaning, relevant meaning, as quantities in this situation, and that's what you're writing out. So it's not just, these aren't just going to be one or two words. There's going to be a phrase or a sentence describing what that quantity is relative to this situation. Okay, so work together on these. Don't, like I said, if you took notes on Wednesday, at the end, don't just start over, practice again, starting over. Figure out what all these quantities are, and then there's some more questions here: input, output, argument, and value of the period. Okay, work together. I'm going to take attendance. Find the quantity t. Where'd you find t? What do you think? What's that? Since when? Yeah, good. Time elapsed in minutes since being at the 3 o'clock position. Since car. Nice, okay. 3t. What quantity is 3t? Quantity is 3t. Yeah.
The angle measurement of rotation of the wheel in radians.
Angle measure swept from where?
From 3 o'clock position to wherever it goes.
And how did you know that it's angle measure? Looking at that function, how did you know that it was the angle measure?
Well, because the angle measure is going to be whether it's in the parentheses of cosine.
Right, so that 3t is what's going into cosine. And we know the input of cosine has to be angle measure swept from 3 o'clock. Right, so that whole thing, 3t, is the input, or what's going into cosine, so it must be angle measure. What about 3? What is 3 in this situation? So if t is the time elapsed in minutes and 3t is the angle measure, that means 3 must be what? Yeah. Nice. So this is the radial speed in radians per minute. So that's how many radians the wheel turns every minute, because then 3t is the total angle measure in radians. And you multiply that by minutes. Okay, cosine 3t. Cosine 3t. Joel?
The horizontal distance in radii that the wheel is traveling.
So it's not that the wheels travel, the horizontal distance of what? Of the...
Horizontal distance of
What do you think? Horizontal distance of what? Of the wheel? So we know it's horizontal distance to the right of the vertical diameter, but of what? So we're going to swing an angle counterclockwise from 3 o'clock. What is it that we're measuring the horizontal distance of? What's that? Yeah, the point on the circle, right? The resulting point on the circle. And in this case, it would be the car, or the person in the car. Yeah. And what will that unit be? So it's the horizontal distance of the car, or the point on the circle, from the vertical diameter in, yeah, so you can say radius lengths or in fraction of a radius. Why? Because it's simply cosine, right? Cosine always gives its values as fraction of a radius. You could say in radius lengths, that's fine. It's fraction of a radius length, or in radii, or in radius lengths. Okay, what is 28? Okay, so it's the radius length of the wheel. And so now if you take the radius length of the wheel and you multiply it by the fraction of the radius length that you are to the right or left, what do you get? Right, so if the whole radius length is 28 meters and cosine is whatever fraction of a radius length we are to the right or left, then when we take that current fraction length of 28, we get the horizontal distance of the car, right, of the vertical diameter in, now we get it in meters. So which of the above is the input into the function? Which of those 6 quantities is the input? They're saying t up here. Agree with that? Yeah, you know that right here by the function notation, right? Function notation tells us the input quantity right there in the parentheses. Okay, which of these is the output quantity? Which of these quantities is the output of the function f? Of all the 6 of these choices. What's that? He wants the last one. The last one, right? Because the rule generates the output quantity, right? The rule, and that's the rule. So this is the 28 cosine 3t. Which of those is the argument? Which is the argument? Right? Argument is the whole expression that cosine is acting upon, or what goes into cosine. All right, so what's the value of the period of the function? So how do we find the value of the period? Well, we know something about cosine. What's the period of just cosine by itself? You just had the cosine function, cosine of the angle swept. What's the period of that? 2 pi. So the definition, first let's do the definition first. Definition of period is interval of, is it the interval of the input or of the argument? Input. Period relates to the input of the given function. It's the interval of input that results in, so it's how much input needs to go by or transgress or transpire, how much interval needs to transpire to get what? A full, so yep, if you're talking about circles, that would be right. A full cycle of output values. How much input needs to go by? How much input needs to transpire? What interval of input so that you get so that the output goes through one full cycle and then starts over again? So is the period of this function 2 pi? No, because the period relates to the input. The period of cosine by itself is 2 pi, but this function is a function of t, and we need the value, the interval of time that results in a full cycle. But we use 2 pi to get that, right? Because we know that if 3t, what's the quantity 3t again? What's it represent? Angle measure, right? That's theta. So what does theta need to do for us to achieve a period, a full period? What does theta need to do to achieve a period? 2 pi. So we need that argument. We need the argument 3t to reach 2 pi. 3t is the angle measure. When that angle measure reaches 2 pi, we've got a full cycle. So what value of t achieves that? You're going to solve for t. What value of t achieves that? 2 pi over 3. So this is a really important way we have to reason about this. We know cosine and sine, their periods are 2 pi. So whatever argument is going into cosine or sine, which is the angle measure, that angle measure has to reach 2 pi. We find the corresponding value of input that achieves that. So when t reaches 2 pi over 3, 3t reaches 2 pi, the cosine has a full cycle. Okay, so let's sketch this. We're going to sketch this function, and so that's something we'll be doing in the next week, is sketching these sine and cosine as they model real-world situations. So let's talk about this. So the first thing we'll look at is the period. So if the period was 2 pi over 3, we just said, let's get a decimal approximation for that. So 2 pi over 3 is about 2 point what? Say it again. 2.09? Someone else get that? Just to confirm? 2.09. And is that, what unit is that? Is that radians? Is that meters? Is that minutes? Is it fraction of a radius length? 2.09 what? Oops. 2.09 what? Okay, the period is the interval of input. Interval of input, and our input is our time elapsed since being at the 3 o'clock position. So it's 2.09 minutes. Okay, sounds about right for a big Ferris wheel that could move pretty good. So 2.09 is right about here. So we're going to mark that off. There, we know that we're going to get a full cycle. This is our time in minutes. And here is our 2.09. So a full cycle, we divide it up into how many sections? If we think about a full cycle, full rotation, we're interested in splitting this up how? How many equal 4, right? So we got 4 quadrants. So we're going to take 2.09 and we're going to divide by 2 first if you want. So divide by 2 first and we'll get a 1.04 or something like that, or 1.05, 1.045. So that would be right here. Okay, so that's our halfway point, and then we can divide that in 2 by again, or take 2.09 and divide by 4, and we'll get what, 0.50, 0.52, right? 0.52. Okay, and then we need the 3/4 mark. So 2 ways to do 3/4 mark. You could take 3/4 of 2.09, or you could just add 1/4 plus a half. You could add those two together. So what do you get when you get that? 1.57. Somewhere right around there. Okay, so these are our 4. Okay, and then we're modeling what? 28 cosine. So again, is this going to be in meters or radius lengths, fraction of a radius? Meters, right? We're taking, cosine gives us the fraction of the radius length times 28, then will give us meters at any given time, right? Meters. So at time equals 0, when the car is at the 3 o'clock position, we're asking how many, what is this asking? How many meters to the Above or to the right? To the right. It's cosine. So it's going to be how many meters to the right of the vertical diameter when time is 0 at the 3 o'clock position? What will we be? 0, 28, or something else? So we're asking, if we start at the 3 o'clock position and time equals 0, how many meters to the right of the vertical diameter will we be at time equals 0? 28. We're at the right side, right? We're at 3 o'clock position means we're 28 meters to the right of the vertical diameter. So here at time equals 0, we're going to plot the point 0, comma 28. And that's actually going to be our, it's going to be like our max, right? You can't get any further than 28 meters to the right if you're on this Ferris wheel. If you do, you're in trouble, right? You're flying off the wheel. So we're going to be 28 meters at the most to the right. And then in the first, as the wheel turns through the first quadrant and you go from the right side to the top, the angle or the time going by is going to be 0.52 minutes. And what is our distance from the, in meters to the right going to be? It's going to go from 28 to, when we get to the top of the circle, 0, right? When we get to the top of the circle, our distance to the right will be 0. So we're going to have something like this, right? And we talked about what? These changes are negative and getting more or less negative. More negative, therefore, are the changes increasing or decreasing? They're getting more negative. These are decreasing changes. They're getting more negative. So therefore, the rate of change is decreasing and the shape of the graph is concave down. The rate of change is decreasing because the changes in distance are getting more negative. Okay, in the second, so from the top of the circle down to the left side of the circle, our distance goes from 0 to what? Negative 28. That's going to be our minimum. And the changes are negative and getting more or less negative. Getting less negative, right? They're negative and getting less negative. So those changes are increasing changes. Increasing changes. Okay, and then what happens then in the third quadrant? Back to 0, right? So we're negative 28, and we go down to the bottom of the circle. Our horizontal distance moves back to 0 from negative 28. This should not be pointed. That's better. Okay, and then in the last quadrant, right? So at the fourth quadrant, we're 0, and then we end up at back to 28. So this is what, tracking out our horizontal distance to the right of the vertical diameter in meters as we're going around. So a point on this graph, say 0.8, whatever that is, negative 22. I'm guessing, okay? I'm just pointing that off. That is, did I just add a point to the graph? Did I just add one more point to the graph? Nope, I just highlighted a point. These are all points, right? When I'm drawing this, I'm drawing lots and lots of points. That's what I'm drawing. So now I'm highlighting one point. 0.8, negative 22. I want you to tell the person next to you, what does that point represent? 0.8, comma, negative 22. What's the meaning of that point? Go.
That's the
let's see here. How about who's the lucky winner? How about Tofi? What does the point 0.8 negative 22 represent? Not sure. Okay. How about Kayla? Oh no. You better know this. Let's see. Cole, what do you think?
It's the negative 22 on the x-axis when it's at 0.8 on the y.
No, that was pretty bad. So we're talking about the Ferris wheel first of all, and then but you switched them. So
I switched.
yeah, switched them. All right. So we got some volunteers here. Elijah.
0.8 seconds is negative 22 meters to the left of the vertical.
Almost one little mistake. One mistake. This is a Ferris wheel. Not a roller coaster, right? You said 0.8 minutes, right? Minutes. So yeah, that'd be a wicked Ferris wheel. That was 0.8 seconds. Yeah. So at 0.8 minutes after leaving the 3 o'clock position, your car is where? 22 meters left of the vertical diameter, okay? So what are points on graphs? They're a coordination of 2 quantities taken together. So in this case, we're coordinating minutes and your horizontal position in meters. So if you take any one of those points, you get a time that's gone by and a corresponding distance from the vertical diameter. Have we made it halfway around yet? No, so we're in the second quadrant. We're almost halfway around. We're negative 20. We're 22 meters to the left at 0.8 minutes. Okay, so let's see how we did sketching the graph. Okay, pretty good except for my artistry. Okay, so we got the right places. All right, and then after 2.09 minutes, you go around again, and you're going to have all the same output values, all the same horizontal distances to the right in meters, and so you get another cycle for the second time around. Okay? Any questions on this example? Yeah.
What was the wording you used for 0.8 negative 22?
Say it again.
What was the wording that you used for the?
You tell me. So what does it mean? So what's 0.8 and what's negative 22? Minutes. Minutes elapsed since the 3 o'clock position. What are we tracking here though? What are we tracking with this function? What quantity? If it's cosine. What's that? Right, which is which? Is that vertical position or horizontal position? Horizontal distance to the from the vertical diameter, right? That's why we're working so hard on writing out these definitions on the last 2 quizzes. So when you see cosine, you know, oh, cosine is going to give me, or that expression of cosine is what? What does that give? What will that always be? Horizontal distance to the right of the vertical diameter as a fraction of the radius. Multiply by your radius length in meters, and you get meters. You're taking that fraction of 28 to the right or left. Okay, so again, so the reason that I have you memorize those definitions and write them out, second quiz in a row today, or Monday, you're going to do that, is so that when you see it in a problem, boom, you know what quantity is, and it's helping you solve the problem. It's not just so you can memorize this stuff over here and then learn how to do the problem separately. Okay, all that memorization is to apply to your thinking. It's a way of thinking about these problems. Okay, another one. So now I'm giving you some setup and I'm asking you to write some functions. See if how we're doing here. Water wheel makes a rotation every 13 seconds. The radius of the wheel is 7.5 feet. The bottom of the wheel is 2 feet. Read carefully. What's the input? What's the input for number 1? What's the input quantity for number 1, for f, function f? Measure of the angle. Measure of the angle. Okay, what is the output of the function f? Vertical height as a fraction of the radius. Okay, that's your clue, right? You got to read and make sense of what you're reading. Input is the measure of the angle swept. The output is the vertical height above the horizontal diameter as a fraction of the radius length. Go, revise if you need to. Only if you get number 1 right are you ready to move on. Get number 1? Yep. Keep going then. Number 1, show me number 1. Good job. Number 1. Okay. So that input and output quantity should be ringing bells, ringing big bells in your brain. Nope. That's the input. Very good. Nope. You gotta make sense of what you're reading. You're just taking numbers and throwing in an equation. Make sense of what you're reading. Yes. 2.5. Good.
So that's we set up theta for t.
Yes. Okay, people, it's ready to catch on. Input theta. What's output? If your input is the angle measure swept counterclockwise, how do we get vertical height above the horizontal diameter as a fraction of the radius length? How do we get that? It's exactly these are exactly the input and output quantities of sine. Input is the angle swept counterclockwise from the 3 o'clock position. Output, vertical distance above the horizontal diameter as a fraction of the radius length. It's exactly what sine theta is. No, what you had to do was make sense of what we've been talking about the last 2 weeks. Yes, that's all you had to do. But if you didn't, then you're not making sense. We've been saying that the input of sine is exactly this: the measure of the angle swept by the point. That's exactly what we said over and over again. And you've written it now 2 quizzes in a row. The input of sine. The output of sine, vertical height above the horizontal diameter is a fraction of the radius length. Okay, so if you struggled with this, then that hasn't sunk in yet. These definitions haven't sunk in yet to the point where you'd recognize, you read that, you'd be like, oh, that's exactly what the input and output of the sine function are. It's exactly what I put into sine, and it's exactly what sine gives me. Okay. So number 2. if we want vertical height in feet, we want vertical height in feet, then what's the input of g? Still theta. But now we just, instead of the output being a fraction of a radius length, we want it in feet. So how are we going to do that? We've got the fraction of a radius length, but now we want feet. So we take that fraction of what? A full radius length in feet. So if the full radius length is 7.5 feet, then we're going to take sine theta is going to be whatever fraction of a radius length we are. We take that fraction times 7.5. If it's a half, then we're halfway up the radius. And we're going to take half of 7.5 to get how many feet? So this goes back to the bug in the fan when we first started. The very thing we started like a week or two ago. We talked about if it's 7.5 feet and you're halfway up, then you're 3.75 feet up. So you're going to take half of 7.5. Okay, H. Now we're going to bring time into it. Okay, so now the input is time. Okay, and C. Let's see. We want the vertical height as in feet. So if it's vertical height in feet, what will the structure of this be? If we want vertical height in feet, it's still going to be the 7.5 sine, right? Now we need to figure out what the argument is. So that argument is going to be something times t, right? It's the radial speed times t. And it says a full rotation every 13 seconds. What is it telling us there? A full rotation every 13 seconds. Therefore, 13 seconds is that's the period. So we need to figure out what this unknown b is so that when t reaches 13, what does bt reach? Right, so when t reaches 13, we need that expression to reach 2 pi. And that will allow us to solve for this value b, this coefficient of t, or the radial speed. So again, that whole thing needs to reach 2 pi when t hits 13 seconds. So b becomes? So b is then 2 pi over 13. Okay, function j. Any questions on that? Again, reasoning about the argument reaching 2 pi, we're looking for now the coefficient. We need that coefficient that creates the situation where when the input hits 13, that whole argument reaches 2 pi. All right, j. Back to blue. So now we want the bottom of the wheel. What? It's a vertical height in feet. So the bottom of the wheel is 2 feet below the surface of the water. So we're going to take our above.
No, yeah, but still need the same thing.
So now we want all our y values, what? To be moved up how much?
2.
I'm hearing mostly 2. So let's go with 2 and let's see how this works. So let's look at quickly here 7.5 sine 2 pi. Okay, here's what you get when you add 2. And we're tracking what? The height of a point on the wheel above the water. How do we do? So let's explain this quickly. So when you add 2, and this is, lots of people blow this on the exam, right? So this is on the exam. Tons of you will blow it, even though I'm telling you that. So don't be one of those people, okay? What just happened? Before we were tracking from the horizontal diameter. And then we just moved up all the y coordinates 2 feet. And what happened? So this is now a point at the bottom of the wheel. Is it 2 feet above the water? No, look, it's underwater, right? It's underwater. So what happened? So if the wheel is here, we want the wheel like this, right? And we want this to be 2 feet. Here's our vertical diameter, or horizontal diameter that we're measuring from. How much does that have to move up so that the bottom of the wheel is 2 feet above? No. So here's our radius, right? 7.5. So in order to get that, we need the center line. The center line isn't 2 feet above the water. The center line then is 9.5 feet above, so that the bottom of the wheel is 2 feet above. So we need to move it up 9.5 feet, not 2 feet. Do you see that? If the bottom of the wheel is 2 feet above, then the center of the wheel is 9.5 feet above the water. So we've got to move it up 9.5 feet. So when I move it up 9.5 feet, there we go. See, now the bottom of the wheel is 2 feet above the water. There it is. Maybe, yeah. Yes.